on, unfortunately. But he and I work together a lot, and we work together on power, which is the topic for today. And what I'd like to do is to just mention to you there are two articles which summarize really the theme of this afternoon, which is how I optimize power to avoid ventilator-induced lung injury. Now, power is one of those buzzwords these days. It's a very hot topic. People are interested in power and how that relates to ventilator-induced lung injury. And before you can understand how to optimize power, you have to understand how power influences ventilator-induced lung injury. Now, I love my colleagues, and especially my junior colleagues, but we don't teach physiology like we used to. You know, and the deep physiology that's necessary to really understand what you're doing with power is, you know, something that's a little foreign to people. So I'd just like to start with a very simple start that I think you will all understand. If we're using constant flow ventilation, we have basically a volume axis during inflation, and we have a pressure axis that has several pieces. The piece related to PEEP, the piece related to the dynamic elastic work of breathing, and the piece that relates to resistive work. At the bedside, at least in America, people are fixated on pressures, the driving pressure, the difference between plateau pressure and total PEEP, and the plateau pressure itself. And we've come up with numbers for what we think is safe or not safe, and that are actually built into a lot of protocols. I think you probably know people don't want to exceed 15 centimeters of water driving pressure or 30 centimeters of water plateau pressure. Now that makes partial sense, but it's not the complete story, because you can generate pressure in various ways at the alveolar level. If we concentrate at the alveolar level, we're looking at this part of the pressure profile and this part of the pressure profile, the static part and the dynamic part. It turns out that pressure alone doesn't damage anything. You have to put it in motion. You have to generate some kind of an energy store that happens during inflation. If we start from end expiratory pressure, let's say a PEEP of 5 or 10, and move up to a plateau pressure, we do, in theory, and during constant flow, and if volume is on the horizontal axis, what we do is we are storing elastic energy in the alveoli all the way to the end of the inflation. Now, I don't know how many of you remember the thermodynamics rules that say that you cannot create or destroy energy. So if you've conserved energy, then you didn't break anything with that energy. Maybe. But what you needed to do to store that pressure is to strain the tissue. And up to a certain point, the strain is very acceptable. If in fact I go over a certain strain threshold, I start to break microfilaments, and we'll come back to this. I'm just introducing it here. We want to pay attention to both volume and pressure, and maybe the rate at which volume is accumulating. Now I'll stop right here and say that this is constant flow, but if I'm plotting volume versus pressure, it doesn't matter what flow pattern I'm using. Volume versus pressure will have the same type of stylized area, and that area is energy. And energy times frequency is what we've come to know as power. It's not really power, but I'll get to that in a second. So there's nothing unfamiliar yet, is there? I think this is all pretty standard. This is from a summary paper that we wrote in the Blue Journal, Patricia Rocco and Luciano and I a few years ago. And the idea here is that you have damaging energy per cycle, emphasis on damaging, the frequency of high stress cycles, and together they produce what Luciano has termed to be power. The energy times frequency. The inflation energy times frequency is power. And that frequency is cycles per minute. Now, it's a very peculiar type of power. And again, we'll touch on that in a moment. But this damaging energy per cycle is influenced by the flow amplitude in its profile, the plateau pressure, the PEEP, and possibly the peak expiratory flow contributes to damage. But that's a fairly sophisticated topic that's still being explored. If you multiply those two together and you exceed a certain level of power, then apply it for a duration of high stress exposure, emphasis on high stress exposure, then you get ventilator-induced lung injury. Let me give you an example. I used to be an athlete, not a good athlete, an athlete. And when I'd run my best and my fastest in what we call the 220 or the 200 meters, you pour enormous amounts of power through your lungs. But the lungs are not vulnerable, and they don't break. They don't injure, not to any significant extent. So vulnerability is very important. And also, the characteristics of the power that you're using are important. The stretches that you're using, the flows that you're using, and the other things we'll talk about. Now, what Luciano has done is given us a summary variable. That summary variable is what he calls power. Luciano is one of my dearest friends, and he understands that term power is actually not the same as what a physicist would say is power. Power is energy per unit time. So if we want to talk about intracycle power, that's one thing, looking within one cycle. But across a minute, it's a cumulative energy collection. There are things that will increase the damaging energy per cycle, amplifiers of stress. And again, we talked about the threshold for mechanical injury. That has something to do with the environment in which the lung is working, and also its innate vulnerability. The frequency of high stress cycles has gotten clinical attention because that's one thing that we can measure along with pressures. Now, we're supposed to be talking back and forth about a case. And I've just set this up so that we can discuss some of the things that are important about power. We've got a 48-year-old male. He's relatively portly, 45 kilograms per meter square, and he's admitted to the intensive care unit with abdominal sepsis. And upon admission, he's febrile to 39.4, hypoxemic and hypotensive with labored breathing. Diffuse infiltrates and bibasilar densities. Antibiotics were begun, 4 liters of crystalloid given with improved blood pressure, but deteriorating oxygenation and mental status, and he was intubated and then ventilated using patient-triggered assist control while at 30 degrees, supine, minute ventilation, 14 liters per minute measured, tidal volume, approximately 7 mils per kilogram predicted body weight, a PEEP of 15 centimeters of water, FiO2 of 0.9, plateau pressure of 35, driving pressure of 20, blood gases 7.28, P to F ratio less than 110, PaCO2 of 45 millimeters of mercury. I think this doesn't look like bad management to this point. We're using a 7 ml per kilogram tidal volume, which is between 6 and 8. The PEEP is 15, that's kind of high, but he's also quite portly, and as we'll talk about in a moment, that's a factor to consider. His minute ventilation is what he's using to achieve a PaCO2 of 45 millimeters of mercury, so that seems reasonable to me. FiO2 is going to be quite high in the beginning, at least, before we were able to taper it. His plateau pressure is above 30, but again, he's got a stiff chest wall. His driving pressure is 20. Again, that's high, but he's got a stiff chest wall. His blood gases, mild acidosis, and PaCO2 of 45. So that looks okay. But now let's re-examine that as we go along. This is the concept that I was trying to get at before. Can you guys hear this, by the way? Okay. If I have a cup of coffee, and I just did before I came in here, and I carry it up steps, I can build up quite a high potential energy. Now, energy comes in two mechanical forms anyway, a potential energy and a kinetic energy, right? If I take my coffee cup up a set of stairs and then drop that coffee cup, I haven't created or destroyed any of the energy. I've just converted it from the potential to where it was originally. But all of a sudden, and that was a damaging force, physicists would call this an impulse, but I'll break the cup and cause a lot of damage. The point is that what has become known as power in the clinical setting is this: inflation, exhalation, inflation, exhalation, inflation, exhalation. And we're doing many cycles, but they're small cycles, relatively small cycles. They're not enormous cycles that would cause a lot of damage. So I like this illustration because we all can recognize that we've broken coffee cups before, we've dropped glasses from up high and broken them, but we don't do that if we do it slowly, carefully, and lift them. The same amount of energy involved, but a different power. Okay. Did I go back? I went back. Sorry. Now, there's one other thing about power before we get into what to do at the bedside. Another concept that we're indebted to Luciano for is the baby lung concept. The idea that some of your lung units are filled and not participating in inflation or gas exchange. And what's left is the size of a lung for maybe a 6-year-old child. He called it the baby lung with Antonio Pezzenti. Fine. So if I use a pressure criterion and I say, okay, this small lung and this larger lung are both being exposed to a certain pressure. I use the same criteria: 30 centimeters of water plateau pressure, 15 centimeters of water driving pressure. I would do the same here and here. But what happens is, unlike the pressure, which is not amplified, simply reducing the size of the capacity of the lung that you're pushing it into amplifies the power. So this is another problem we have to contend with if we're trying to use power at the bedside and assign a numerical value, right? We don't know what the baseline gas volume is of the lung we're dealing with. Years ago, one of the companies came out with an FRC measurement, a gas dilution measurement, that never took off really, never captured people's ideas at that time. And I don't know if they're interested now or not, but it's something that we need to know. How big is this baby lung we're talking about? Is it a small baby or is it a big baby? Because power and energy and force are amplified by a shrinking baby lung. And if you want to read about that, we wrote this paper a couple of years ago on that theme. So power has a lot of interesting little features that we need to master, we think, at the bedside. Now, this is one of my oldest slides. When I was interested in the work of breathing that people do, during constant flow inflation, There's work to inflate the chest wall, which is the area C. Remember I told you that energy is volume and pressure. That area quantifies the work of breathing and also quantifies the energy that you're applying with your ventilator. So C is the work to inflate the chest wall, and that appears in what clinicians will measure at the airway opening. We can only measure one point here. Now with EIT and other methods, okay, you can hang me up and say, you know, we could do better than that. But if you're just looking at the bedside and writing orders and saying, you know, what pressures and what flows and what PEEPs and such we use, we are confronted with an airway pressure that looks a lot like what I've drawn here in red. So here's the work to inflate the chest wall. This is the elastic work of lung inflation. And in a patient who has obstructive airways disease, this is the resistive work of breathing. This is the flow-related piece that we can manipulate as we change the IDE ratio, for example. Now, what do you do with something like this, where the chest wall is enormous? It may not be as stiff as you think it is, but it's stiffer than normal for sure. And if you try to measure at the airway opening and just use the airway opening pressure and the airway power and so on, you may be dealing with quite a small lung to start with, even if it's not diseased. It's compressed. It's a baby lung in a sense, not even if it doesn't have ARDS, right? And he's got a lot of chest wall work to do with every inflation. So what do we do with our pressures and what do we do with our other parameters? If you want to drop an esophageal balloon, you can get a rough estimate of when it, you know, you've recruited most of the recruitable dependent zones, but you're still left hanging a little bit, so to speak. And I don't mean to talk down to this audience, but I think you know that if I have the same alveolar volume to deal with, I can be measuring 10 centimeters of water, 20 centimeters of water, or 30 centimeters of water at the airway opening, depending on whether I have a very stiff chest wall or if I have a normal chest wall and a passive situation, or if I have active situation, I'm going to have a very different setting. So if somebody says, Dr. Marini, how much power do you use? Well, I first have to say, what does the chest wall look like? Is the patient breathing by himself, or are we paralyzed? Because if we're paralyzed, then I can give you an estimate of what the work is for the lung and the chest wall together. And if I drop an esophageal balloon, I can get a handle on what the stresses are across the lung itself and the power is. Okay. We all understand that, I think. Now this is a little bit more sophisticated than, well, it's not difficult. It's just a little more interesting from a VILI point of view. We've got tidal volume on the horizontal axis. We've got pressure on the vertical axis. Notice I didn't say just volume. I said tidal volume because I don't know what the size of the baby lung is. All I know is what I'm measuring with the volume I'm pushing in and the pressure that's being generated, right? Now, in power, as we understand it right now in the literature, Luciano's power, and I keep on bringing his name up, he's supposed to be here and we're supposed to be conversing, but this whole block of elastic work, this is the total work from the dotted line all the way down to the base. This is the elastic work, the dynamic piece, and the static piece. There's going to be a point at which we reach a threshold of alveolar pressure where some of the lung units are being stretched so far that the matrix elements that separate the alveoli are being fractured. I'll show you an image of that in just a moment. So it's not just the power, it's not just the intracycle power. You know, if we want to be a little more careful, we could talk about intracycle power. There's an unsafe block of energy and there's a safe block of energy, depending on what the threshold pressure is. And that's going to vary from bottom to top of the lung. Okay, down here, if I'm talking just about stress, just about stretch, not talking about any amplifiers or stress amplifiers or anything like that, then down below I've got small volumes. Up above I've got a higher volume, something closer to my pressure threshold at which the matrix elements begin to break. Point here is that when we talk about intracycle power, and I'll speak about that later in the meeting, but when we talk about intracycle power, we've got to understand that we also have to look at the pressures that are being generated at the alveolar level so that we get an idea of what is a safe energy and what is not a safe energy. I think this is a pretty good way of looking at things. If we look at total power, okay, this is from a paper that I just published with in Critical Care, John Lewis Journal. If you look at the cumulative power on each of these illustrations, you have equal total power in each pattern. Here the respiratory rate is 16. The cumulative power that's above the threshold pressure is 0. The threshold is the blue dotted line. Here I've got a respiratory rate of 16. I have some of the tidal volume that is occurring above the threshold level. And so these little triangles are the potentially damaging piece. If you want to think conceptually, what is the safe energy, what's the damaging energy? It's going to be this whole block, this part above is a damaging bit of energy, and down below we have an energy investment that's also at risk. And this is relatively new stuff to think about. Experimentally, we have very little data to back it up. I'll say it right now. Okay, so here we've got a cumulative power, driving power, that's greater than 2.5 joules. And here we have a respiratory rate of 10. So I've dropped the respiratory rate. I've increased the amount of intracycle power per cycle. And the cumulative driving power above 2.5 joules is also just as great as it was here, even though we dropped the respiratory rate. What's the point? The point is that the characteristics of the individual cycle are important, the threshold's important, and the frequency's important. So you got to think in three terms: the pressure, the energy that's above the delivered above the pressure, and the frequency of that delivered energy. Any questions at this point? Is it all clear? How can you measure the threshold? Okay. Well, if you're talking about the average lung, and you're talking about clinicians' terms, then 30 centimeters of water would be represented by the blue line, okay, of plateau pressure. The driving pressure would be less than that. It would be 15. So the average number would be 30 or 15, depending on whether you're focused on the plateau pressure or the driving pressure. Okay? Some people... Sorry? Yes. Well, that's the threshold at which the power then delivers. Any further increase in tidal volume and pressure will contribute to damaging energy. And here, there's more of that going on per cycle, but you've got fewer cycles, but the cumulative amount is the same, because the frequency times the intracycle damaging power is what we're concerned about. I don't want to get too hung up on all the details, because the threshold pressure is going to vary depending on your position, on your position in the lung, and the fragility of the lung you're dealing with. But in concept, it's not the entire power that you're talking about, it's the damaging power. if we talk about the matrix elements, and this is from our lab a number of years ago, the matrix elements are actually fibrillar in nature. And if we deliver enough damaging energy per cycle to break a few of the weakest links, it loads the other ones in the sequence. It loads the other filaments. And then the weakest ones then break as well, and you get a shrinking baby lung. So it's like taking a rope with a frayed piece that progressively will experience increasing breaks until it finally ruptures with advancing cycles. So the number of cycles is important, the number of cycles above a damaging pressure threshold to break the matrix. Is that clear or not clear? Okay, so it's not the total power for a number of reasons we've talked about. The chest wall, the effort, when you try to fix a numerical value, you're going to get into trouble. In the same patient, you can look at a trend, but between patients and trying to compare absolute numbers, you're going to get in trouble. So we're coming to the end now, so you can breathe deeper. How I optimize power to avoid VILI? My first priority is to reduce the vulnerability to VILI and the body's needs for ventilation, oxygenation, and blood flow. The demand side. That's the overlooked part of so many of our clinical situations. We need to know what the demand element is and whether we can adjust that. And once demands and co-contributors to vulnerability are minimized, ventilator settings assume the top priority. In descending order of importance, those settings are as follows: driving pressure and PEEP, minute ventilation, which includes frequency, and inspiration to expiration ratio and flow profile. The flow is important for reasons that it distributes the power within the lung. But it's in third place behind the frequency, the minute ventilation, and the driving pressure and PEEP. Whether non-invasive or invasive ventilation, I attend first to transpulmonary plateau pressure and transpulmonary driving pressure, and then ventilating frequency and minute ventilation. I monitor the latter as a key component of power and a helpful indicator of ventilatory efficiency. Allowing hypercapnia to a PCO2 of approximately 60 promotes reductions of the frequency of minute ventilation and ventilating power. Okay, you can read about this, but basically reduce the demands, try to reduce the vulnerability, and in sequence, get the driving pressure and PEEP right as low as you can, minute ventilation, and inspiration to expiration ratio and flow profile. So, are there any changes to make? These were our original choices, and we thought they looked pretty good. Okay? And as we look through this, we can say that there's at least 10 adjustments that we can use. You may disagree with me, and I hope you do, but you've got a very heavy-set guy admitted to the ICU with abdominal sepsis. Upon admission, he's febrile to 39.4. You need to bring that down to less than 38 if you can to reduce the demands. He's got diffuse infiltrates with bibasilar density. Antibiotics begun, that's good. You volume resuscitated him, that's good. Blood pressure's okay, oxygenation deteriorated. Well, he's 30 degrees supine. I would put him in the prone position using patient-triggered, paralyzed, not assist control, but controlled ventilation at this point. Decelerating with an IDE ratio not of 1 to 2.5, but 1 to 1.25 if I can, something closer to 1 to 1. A square wave profile, probably in preference to a decelerating profile of the flow. Minute ventilation of 14 liters per minute with a lung this sick is probably not good. You need to bring that minute ventilation down, even if the blood gases show you that his PCO2 goes up to 60. In the prone position, you're likely to get an FiO2 that's less than 0.9 and still achieve your goals. Your 35 centimeters of water plateau pressure, it would be nice to bring that less than 30. and and how to adjust PEEP the least needed for the PaO2 that you're trying to achieve in this particular patient. So I can count 10 things that I would do differently at the bedside when I have in mind the power and the vulnerability. The vulnerability is, and the demands are really a very important feature, which, I tried to touch on, but it's underemphasized. Last thing, you just heard a nice presentation by Dr. Combs and colleagues. In the future, if we can reduce the minute ventilation requirement with extracorporeal support, as we did during COVID, and do it more effectively and less expensively, I think that's a strong way to go. And that's the theme of the resting baby lung that Luciano's been working on since the late 1970s. And this was taken a couple of years ago, but it's a consensus of two. I was trying to reach a consensus of two at the end of the debate, but unfortunately he wasn't here to participate. Any questions that I can answer? Oh boy, here we go. Okay, let me start over here. Yes, sir.
So it is fair to say that driving pressure in PEEP modulates the amplitude of intercycle power?
Yes.
And why you choose the square shape?
Because what I have not described is the rate at which the power is being delivered. The rate at which power is being delivered influences viscoelastance and stress amplifiers and things that I did not want to get into in an lecture like this, a box like this. No, you're putting me in a box, sir. I'm sorry. But I think you understand that the faster you put a given amount of energy in, the more likely it is that you're going to overstretch the vulnerable pieces of the lung, which is always heterogeneous in its mechanics.
The squares to modulate the speed that you're delivering.
That's correct. That's correct. Okay. Yes, sir.
When you show us the curves, it was the total airway pressure. For example, in that patient that has an abdominal infection, the stiff chest wall, do you think there's any utility in separating the components? Because the chest wall will burst, and you can put a lot of power, but if that power dissipates in the chest wall, the alveoli won't have any problem. So, do you have any focus in those particular kind of patients, like intraabdominal pressure or very obese patients?
Your point is very well taken. That one of the reasons why I did not say that there's a numerical number that I would be using is just for this reason, that you may need to use 18 centimeters of water of PEEP or higher to get the flexible recruitable pieces recruited, the baby lung expanded in a good way, not overdistended but expanded. And if you read a classical paper you probably have by Peter Suter and colleagues many years ago, where he looked at what's the optimal PEEP or the best PEEP, and it was where the compliance was the least for a given tidal volume, which means the driving pressure. So if you're using the same tidal volume and the driving pressure is minimized, you may be doing about as well as you can to guess what kind of tidal volume, what kind of tidal volume and driving pressure you need to use. But, Dan Telmore, who's here at this meeting, had that famous paper that showed that, if you could make the transpulmonary pressure 0 instead of negative, then you would have the best chance of recruiting all the lung. Okay? Yes, sorry.
Please, what would be your oxygenation target in this patient?
Oh, that's a very good question, because it depends on what his chronic PaO2 is and what his heart status is, what his right ventricular status is. Things that we're just beginning to rediscover the heart. Michael Pinsky was here earlier with Jean-Louis Thibault, and I'm sure they would agree. We've got to pay much more attention to what's happening with the heart when we talk about lung protection, because lung protection doesn't necessarily work. Anyway, to answer your question, I think that if you're I can't give you a precise number, of course, but if this guy was chronically hypoxemic, which he might have been, then, I think an oxygen saturation of 88% or 90% may be good enough for him. And I can't give you a precise number, but I would do an ultrasound if I could, and to look at the right ventricle. Did I confuse the heck out of everybody? No, here you go.
Is it correct to say that peak is one of the most important determinants of mechanical power, and probably this patient need for esophageal balloon at bedside to better understand the mechanical of the lungs?
In a very obese patient like this, I know what Luciano would say: drop an esophageal balloon and try to get the information about the lung at the level of the balloon, and try to get it, the driving pressure of the lung as low as it can be for the tidal volume that you select to use. So I don't know if that answers your question. No.
I mean, probably we need for the esophageal balloon at the bedside.
Yeah. Yes.
Monitor more patients.
More patients like this, absolutely. And that tells you much more about what's happening with the lung itself. And, we haven't talked at all about positional change, but positional changes will make a big difference in not only lung recruitment, but for the same pressures, but also, or higher pressures, if you turn patients prone. We learned a lot during the COVID experience with belly pushes and that kind of thing, actually improving things and not hurting things. But yeah, yes, ma'am. I'm sorry.
How does the IE ratio affect the power? Because you also change the IE ratio.
Right. It's related to the question that was asked earlier about flow. Yeah. So the longer you can make the IDE ratio without going to extreme inverses and raising mean airway pressure too high, the slower the flow, average flow needs to be. And the slower the average flow needs to be, probably the more uniform is the distribution. That's the idea, to minimize the viscoelastic forces, which are amplifiers of the stress and strain.